Now let's look at some examples using Euler's method. To begin with, suppose we're asked to use Euler's method with delta x equals 0.2 in order to estimate the value of y at x equals 1 if dy dx is known to be 2x and y of 0 is known to be 2. So notice we're given an initial value problem, and we're also given a desired x value at which to approximate the solution. And importantly, we're also told what step size to use. And we're going to see that we have to start off the problem with an assumption of that step size. So we can see here that I'm starting at x equals 0, and I need to end up at x equals 1 with jumps of size 0.2. Now, we're essentially going to find these different linear approximations in succession, just like I demonstrated in the previous video. However, there is a way we can organize that in a slightly nicer way that involves a table of values. So I can collectively look at my xk values, my yk values, I'm going to call it my slope values, and my last column I'm going to refer to as rise. So to be clear, K here is just kind of telling me what step I'm on. So with regards to this table, there's certain things that I'm going to be able to fill in right away. Leave myself some space. And let's see. So we know that we have to be given an initial condition. So in this instance, I'm able to fill in the 0 and the 2 right away. And then the other thing we know is exactly what our x values are going to be, because we know that we're starting at 0, we're using step size of 2, and we need to end up at 1. So to be clear, my end result is going to be whatever I fill in here. We want to know when x is 1, what do we estimate the y value to be? And so the way that we're going to fill in this table is by working our way from left to right and then down on these rows here. So how do we fill in those rows? The way we're going to do that is essentially using exactly what we have with regards to the linear approximation. So the slope, I'll point out, that refers to dy dx, and the key thing is we need to update it for each row. Now for this particular example, dy dx only depends on x. So in order to find the slope, I take 2 times whatever my current x value is. In this case, that's 2 times 0. And then finally, the rise, what we're looking at here is the information to tell us how far we're going to move up from our current y value, in this case 2, to predict the y value at 0.2. So to think about the rise, we can think of, just a quick image of a slope here. So if I have this idea, and we're looking at here, if I think of this as the rise, one might argue that's delta y. The run here is delta x. And what we're thinking of as dy dx is, of course, roughly approximating or approximated by the secant slope here, not claiming those are equivalent. But we can say that dy dx is approximately delta y over delta x. And therefore, if I wanted to estimate the rise, or my delta y, I can do so if I can take the derivative and multiply it by the run delta x. So this final column here is dy dx times delta x. So notice that means to get this last column, I always take the column directly to its left and multiply it by your fixed delta x. So in this last column, I'm always going to take my third column times 0.2. So here, that would leave me with 0. So now we've completed one row, and what we're immediately able to do is use that information in that last column to update my y value. So this is telling me that to get the new y value, I take the old one and I tack on the rise, and I get the new value, which just happens in this instance to be the same as our previous value. So now we think about in this row, x is equal to 0.2. The slope is 2 times x, 2 times 0.2, which gives me 0.4. The rise is 0.4 times 0.2, which yields 0.08. So now to get my new y value, I take the previous one of 2 and I add the rise and I get 2.08. Now x is equal to 0.4, so 2x is equal to 0.8, and the rise is 0.8 times 0.2, which gives me 0.16. To find the new y value, I take 2.08, the most recent y value, and I add to that 0.16, giving me 2.24. Here, x is equal to 0.6. So dy dx is 2 times 0.6, or 1.2. And finally, I take 1.2 times delta x to get the rise, and that gives me 0.24. So my new y value would be 2.24 plus 0.24, which is 2.48. 2 times the current x value is 2 times 0.8, or 1.6. And I take 1.6 times 0.2 to give me the rise. And finally, we're in that last step where I take the most recent y value, 2.48, and I add to that 0.32, and that gives me 2.8. So this is the answer we're looking for here, an estimate of the value of my solution function when x is 1. So we can see that from this technique, I get that final approximation. But the other thing we get all along the way is that we get this collection of y value, coordinate pairs. So for x equals 0, 0.2, 0.4, 0.6, 0.8, and 1, we are actually getting here a kind of a picture here of exactly what y values go with those, and that would allow us then to be able to sketch out this resulting solution function as well, like an approximation of that. Notice that we don't actually end up needing these cells because in some sense, those last 2 columns are always used in service for finding the next y value, and we're done when we get to this final row. So a couple things I want to point out that are going to be true in general. First is that a smaller delta x, or step size here, generally yields a better approximation. So that's in line with a lot of ways that we've looked at approximations previously. So that's important, but also to consider here, if the solution function, y of x, is concave up on the interval of interest, so in this example from 0 to 1, then Euler's method underestimates values of the function. And the opposite is also true. If the solution function is concave down on the interval of interest, then in that case, Euler's method overestimates. So you can see if it's changing concavity throughout that interval, all of a sudden this notion of knowing that we have an over or an underestimate gets lost. So you might ask, well, how do we know if the solution function is concave up or concave down if the whole point of this technique is that we can't find the exact solution? Well, there are several ways we can do this, and in particular, we can actually look at the original differential equation. So in the above example, knowing that dy dx is equal to 2x, I can take the derivative with respect to x of both sides, and that's going to tell me that the second derivative of y with respect to x is 2. That's constant, so we know that that's 0, or excuse me, that's positive. I'll point out, if it wasn't a constant, the key thing is we would need it to be clearly positive here, at least on the interval from 0 to 1. This is concave up everywhere, so y is concave up. And what we get from that information is that we assume now that y of 1 is at least 2.8. That was our predicted value, but now we know it's an underestimate. And so we can see here from the first note, the idea that if I had gone from my delta x being 0.2 to say 0.1, we would expect that we would get a better approximation of the true value of this solution function at 1. But I'll also point out that to check the concavity, so we see here just using the differential equation, we can get that right away. But you could also look to the table. So you could plot the points that we get out of this from x equals 0 to x equals 1. And again, you could look then at the general picture of that graph. And then the other thing we could do is also look at the slope column, so that's third column. Notice that these slope values are positive and they're also increasing. So that's enough for me to see that that is going to mean positive second derivative as well. So those are just a couple ways that you could get toward analyzing the concavity. Okay, so of course, the other thing I'll point out with this differential equation, it's worth noting that we could, in fact, solve this exactly in order to solve for y. So this really wouldn't be a great example of when we would need Euler's method. However, it does demonstrate the process. I want to go through another example where we don't currently have the tools to solve the differential equation. And the other thing that I wanted to make sure is clear is that we can still use this technique even when the derivative depends on both the independent and the dependent variable. In our previous example, it only was expressed as a function of the independent variable. So here I want to use Euler's method. My delta t is 1. My initial condition is y of 0 is equal to 1. And dy dt is defined to be t squared plus ty. So I'm going to use the table in much the same way as I did before. So I'm going to name my columns here. And start to fill in again what we know. So I'm given the initial condition, and we want to move from 0 to 4 with size 1 steps. So 0, 1, 2, 3, 4. I know that that's as far as I need to go. And now I can start filling in the rest of the table. So when we get to this column here, again, I want to point out that what I'm really thinking of is t squared plus ty. So in this first column, t squared plus ty is going to be, maybe I'll leave myself a little bit more room here. So t squared, so t is 0 here, so we'd have 0 squared plus 0 times 1. Of course, that's 0. And when I get to this last column, recall that I take the slope, 0, and I multiply it by delta t, which is 1. So whenever your delta t is 1, it should always be the case that these last two rows are exactly this, last two columns are exactly the same. So that means now that my new y value is the old one plus my rise of 0. So I stay right at 1. Now I compute t squared plus ty when both t and y are 1, and I'm going to get 2. To get the rise, I take 2 times delta t, I get 2. So now my new value is I take the old one of 1 and I add 2 to it, and so I get a y value of 3. Here t is 2, so we have 2 squared plus 2 times 3. I get 10, and of course 10 times delta t is still 10. My y value is now 3 plus 10, or 13. And computing the slope now, we have 3 squared plus 3 times 13. And that's going to give us 48. 48 times 1 is 48. And now finally I take the 13, I add 48 to it, and I get 61. And again, that is going to be the requested approximation. If we were then asked a few more things, we could say, is this an over or an underestimate? Then recall what we really want to check is the concavity. So we're starting with the knowledge that dy dt is t squared plus t times y. So if I now want to take the second derivative, again, with respect to t, that's going to give me 2t. And then recall that y is a function of t, so I really have to use the product rule on ty. So that would give me 1 times y plus t times dy dt. Of course, note that we know exactly what dy dt is. That's given in the problem. So I can replace that, 2t plus y plus t times t squared plus ty. So we're getting here that our second derivative is 2t plus y plus t cubed plus t squared y. So to look at this, notice that all of our t values and all of our predicted y values are positive. So this is greater than 0 for certainly both t and y greater than 0. And so this means that on our interval of interest, we know that our solution function is concave up, and then consequently y of 4 has to be at least 61. And suppose now we're asked the following question, still with regards to this example. If we instead used delta t equals 0.5 rather than delta t equals 1, we could ask, would our estimate increase or decrease? So thinking about that here, we can recognize that we know we would still have an underestimate because we still have that on that interval, the solution function is concave up. So the key thought process here is that both would give an underestimate, but with delta t equaling 0.5, the approximation is more accurate. And so that would imply that in answer to this question, our estimate would increase. So if I have two underestimates, the more accurate one is larger. So this is just putting to use several of those ideas about Euler's method in general, both 1 and 2, in order to answer that question.